Welcome. So we're going to be reviewing significant figures and then putting that into some equations. So the rules: any non-zero number is significant. 1, 2, 3, 4, 5, 6, 7, 8, 9, significant. Leading zeros are never significant. Leading has an L in it for a left side. That means to the left of the first non-zero. So my first non-zero is here. So if I had any zeros over on this side, those guys would be leading. Leading are never significant, right? And so one of the reasons why, as you can see here, it's not needed. There are other cases where it's needed as a placeholder, but they are still not significant. So it doesn't matter if there's a decimal involved or not. Leading are never significant. Contained zeros, those ones are trapped between two non-zeros. So I have a non-zero of 1 and a non-zero of 2. So this zero here is contained or trapped. So he is always significant. It's only between two non-zeros. Okay, this decimal place is not a non-zero, so there are no other trapped or contained zeros in this problem. Trailing zeros, trailing has a right. So that means to the right of the last non-zero. So in this case, the 2 is our last non-zero. So to the right of that is our trailing. Notice the leading and the trailing and the contained, they're all within a group. So it doesn't matter, again, if there's a decimal place for determining if they're trailing or not. All the zeros to the right of the 2 are trailing. And now let's see what's the weird rule with trailing. Trailing zeros are sometimes significant. If you physically see the decimal place, they're significant. The decimal place can be at the start, can be at the middle, can be at the end, anywhere in between. You have to physically see it, not know it's there. You have to physically see it. If you see it, then they are significant. So let's go through and count. The 1 and the 2 are non-zeros because they're between 1, 2, 3, 4, 5, 6, 7, 8, 9, significant. There are no leading zeros, so those are not ones we have to worry about. Contained are the trapped zeros, so trapped between the 1 and the 2, they are always significant. So you put a little underline to say, yes, I know this is significant. Trailing zeros are the zeros on the right, so the 0.0. They are sometimes significant. Since we see the decimal place, they're significant, so they get underlines. So 1020.0, all of those numbers are significant. So there is 5 sig figs in this answer. How about if we have to do it in a problem? If you have a multiplication and or division problem, you're going to round the calculator answer to the least sig figs. That is your next rule. So we have 1, 2, contained, trailing, see the decimal place. So quick review, that one has 5 sig figs in it. 25, non-zero, non-zero. This guy has 2 sig figs. Round to the least sig fig. So between 5 and 2, we're going to be rounding our answer to 2 sig figs. The calculator answer of 1020.0 times 25 is 25,000. This is my calculator answer. I have to round that answer to the least sig figs, which was 2. Underline the first 2 sig figs, because you've got to do that. If there's leading zeros here, you don't want to underline those. That's going to mess up your whole answer. So you got to underline the first 2 sig figs. In this problem, it's the 2 and the 5. Now switch over to your math brain, and the last underline is your rounding point. So just like when you take those math assessments, round the answer to the underline. You just have more than one. You just always look at the last one. That last underline is in the thousand spot. So we're either rounding down to 25,000 or we're rounding up to 26,000. There are no other options. You're not rounding to 25. You're not rounding to 26. You're not rounding to 25,500. We are rounding to the nearest 1,000. You're now totally in math brain. Okay. And how do I do that? I look over here. If it's a 5 or greater, then you are going to round up. So our answer is 26,000. And then when you get your answer, just go back and double check, make sure you didn't make any silly mistakes. 26,000. The 2 and the 6 are significant because they're non-zeros. These guys are all trailing. Why? They're on the right side. They're grouped together. Do I see a decimal? Nope. I see a comma. A comma is not a decimal. I don't see a decimal. So even though I know there's a decimal there, I do not see them, so it does not count. So those trailing zeros are not significant. 26,000 is still my answer, but the number of sig figs is 2. So be very careful on your rounding. All right, so here we have a density problem, mass over volume. They gave you the equation. They might not, because it is a standard from earlier years. The mass of something, I'm going to substitute. They give us a mass of 1.25 grams. They gave us a volume of 0.010 liters. So if I solve this problem as it is, I would get an answer in grams per milliliter, because grams would be on the numerator and liters would be on the denominator. Read carefully. For this problem, we're using grams per milliliter. That means I cannot use this guy. I have to convert him first. So I got to convert 0.010 liters into milliliters. Dimensional analysis. I always start with my known over 1. So I just rewrite that over 1 and then times my next fraction. What is my pathway? I'm going from liters to milliliters. We always divide the from, multiply the 2. So I'm dividing out the liters. So it goes on the denominator, the divide sign. I'm multiplying in the milliliters. So that goes on the numerators. And now what is my unit conversion? From my metric ladder, I know 1,000 liters is 1 milliliter. So the 1 is going to go at liters and the 1,000 is going to go at milliliters for my, what's this called? Unit conversion. And that gives me an answer of 1 milliliter. How is it milliliters and not liters? Because I had liters in the numerator and liters in the denominator, so those units divided out. Then I plug this in and I get 1 milliliter. This was a multiplication division problem. When you have dimensional analysis, you are going to round to the sig figs of the known for year 1. Not significant, not significant, not significant. Why? They're leading. Doesn't matter that there's a decimal. Does not matter. Leading or never significant. The 1 always significant because it's a non-zero. How about this 0 guy? That guy's a trailing. He's only significant if I see the decimal. Does not matter that I see the decimal way over here. If I see the decimal anywhere, he's significant. So I need to round my answer to 2 sig figs. 1, I can't just add a 0, that's 10. 1 and 10 are 2 totally different things. But I can add a decimal place, 1.0 milliliters. Non-zero significant, if I see the decimal, trailing significant. So the volume I'm going to use for the problem is 1.0 milliliters. So now my answer is going to be grams per milliliter. Great. So now I'm going to divide 1.25 grams divided by 1 milliliter, and I get 1.25 grams per milliliter. That's my calculator answer. 1, 2, 3 sig figs. Not significant, not significant, not significant. Leading or on the left, they are never significant. Significant, trailing. Trailing's on the right is significant if I see the decimal place. 2 sig figs, which we already figured out over there. Yeah. So 3 sig figs and 2 sig figs, I got to round my answer to 2 sig figs. So I have 1.25 and I need to round it to 2 sig figs. 1.25, 2 sig figs. So 2 underlines, the first 2 significant problems. So 1 and the 2 are significant, so they both get underlined. And that makes my rounding point here because we round to the last underline. This point is either called the 1 decimal place point or it's called the tenths. round to the nearest tenths. So we're either going to round down to 1.2 or round up to 1.3. I look at the next number, it's a 5. 5 or greater, we round up. So my answer is 1.3 grams per milliliter is the density of this sample. Go back and double check. 1.3, the 1 and the 3 are non-zeros. 2 sig figs. All right, I did it correctly. What if I have addition and subtraction? When you have addition and subtraction, you are rounding to the least decimal place. So it's a little bit different here. You're still going to do the same exact process, but instead of counting sig figs, you count decimal places. 2 decimal places, 1 decimal place, 2, 3, 4 decimal places, 1, 2, 3 decimal places. Round to the least decimal places. So my answer has to be rounded to 1 decimal place. Find the calculator answer. And where's my 1 decimal place? The 5. The tenths is the 1 decimal place area. So I'm rounding, in this case, to the 1 decimal place. Always check every single time. Your rounding point can be different. So I'm either going to round down to 6.5 or round up to 6.6. I look next. It's a 7. Round up. So my answer is 6.6. 6.6. 2 non-zeros. Double check. Yep. 1 decimal place is in my answer because that was my rounding point. All right, calculate the molar mass of C6H12O6. So if it's been a while since you've done molar mass, remember you rewrite these problems. I have 6 carbons, 12 hydrogens, 6 oxygens. So when I do my molar mass calculation, I want to calculate using 6 carbons, 12 hydrogens, and 6 oxygens. We just read it right off. There are 6 carbons, and there are 12 hydrogens, and there are 6 oxygens in my sample. I'm going to add some parentheses here so it's easy to see where I'm going to have to substitute. Carbon on the periodic table, 12.01. Oh, and actually, if they gave you masses on here, okay, the Virginia SOL typically uses 12.01 for carbon that they gave us in the chart, 12.0111. So I'm going to use the chart. Yeah, it's like use the force. What they give you, that's what you're going to use. So I'm going to use hydrogen 1.00794 and oxygen 15.999. So now I'm going to find this answer. Remember, it's like algebra. So it's 6 times 12.0111. 6 times 12.0111 plus 12 times 1.00794 plus 6 times 15.999. Remember, you can always pause and see if you get the same answer as me. You can try your rounding as well. This would still count as adding and subtracting. These 6, 12, and 6, those are exact numbers. There are 6 atoms or 6 moles of carbon. So it's 6.00000. So you're not going to use that in your calculation. So we're mainly concerned with the fact that we are adding and subtracting. So use your adding and subtracting rules after you find the calculator answer to see if you have this concept down. And that's where that pause button comes in super handy. So I'm getting 1.6 or 168.632881. That is my calculator answer for the molar mass. So I'm going to use grams per mole for my molar mass. Okay. What is the rule? Adding and subtracting, least decimal place. 1, 2, 3, 4 decimal places. 1, 2, 3, 4, 5 decimal places. 1, 2, 3, 3 decimal places. So I'm going to round my answer to 3 decimal places. 1, 2, 3. So I'm going to round to the nearest thousandth or to the 3rd decimal place. I look next, it's an 8. So I'm going to round up 1 168.633. I could either round it down to the 2, but that 8 tells me I'm going to round up. So my molar mass is 168.633. Now, that is what we had to do in the problem based on the rule of sig figs. Virginia SOL typically wants 2 sig figs, or 2 decimal places. So if they're still using that rule with the new standards, you would be rounding to this place instead. Okay, you'd be rounding to the hundredths spot or the 2 decimal place spot. You look over, that's a 3, that's a round down, 168.63. That would be the answer if you're rounding to 2 decimal places. So just be aware of the different requirements that it could give you. Okay, so now sometimes in the standard, you're going to see a graph that you have never seen before. That is okay. Take time to analyze it. I see reaction rate is on the y-axis. I see temperature in Kelvin. That's what that K is, Kelvin. Okay, that's the absolute temperature scale, and that is on the x-axis. You might remember dry mix. So we know that the dependent variable is reaction rate, and the independent variable is temperature. What else do we know? Rate of chemical reaction. So you might remember the word rate basically means speed. What is the speed of the chemical reaction? So as we increase the temperature, so at 295, we have a reaction rate that equals this number here. It's okay, there's no scale on it. That's all right. If we increase the temperature to 305, then we have a higher reaction rate. As the temperature increases, our reaction rate increases. Okay, and this one is probably not directly proportional, but we need a little bit more data before we could answer that question. So just take your time if you get a graph, and have a great day.